Welcome to this video on pH calculations. We're looking at the pH of strong bases. Remember, our first question in all of this is trying to ask ourselves, what is the situation that we are facing? So how will you know that you're in a situation where you've got a strong base? Well, strong bases are metal hydroxides, so you're always looking in a strong base pH calculation for something hydroxide, and it should be a metal on the front. And in addition, they need to be highly soluble in water, and we'll see why in a second. So the most common ones are these group 1 hydroxides, so things like sodium hydroxide, potassium hydroxide. They're probably 1 and 2 in terms of most popular, but you could have things like rubidium, cesium, lithium hydroxide as well. Now the group 2 hydroxides are nowhere near as soluble, so the solubility limit for magnesium hydroxide is 0.00011 moles per decimeter cubed. So if you have any solution that's more concentrated than that, it's not going to be fully dissociated. There's going to be some insoluble magnesium hydroxide. Calcium hydroxide will work up to a concentration of 0.23 moles per decimeter cubed. And barium hydroxide will work up to about 0.3 moles per decimeter cubed, and that's working around 25 degrees C. So other metal hydroxides tend to be insoluble. So you might remember back to doing experiments where you actually precipitated some of these hydroxides, like iron hydroxide, copper hydroxide. They tend to be very, very insoluble. So really we're sticking mainly with things like sodium and potassium hydroxide. You've also got to be really careful to watch out for ammonia, or ammonium hydroxide. Now this is a chemical which is common, it's used, but because of the NH4, the ammonium ion, being somewhat acidic, this is actually going to release some H+ ions as well. It's not just like something like sodium hydroxide, which just releases OH-. So this one is not a strong base. The other way of thinking about it is ammonia itself is weak. So it doesn't produce as many hydroxide ions as there are ammonia molecules, far from it. So please be careful with that one. Bottom line, if you're doing A-level chemistry, at the moment, at least with the OCR specification, which is what we teach, there's no requirement for weak bases. So if you see something that's got hydroxide in, it's pretty much, and it asks you, it's going to be a strong base. But do be aware of ammonium hydroxide. Secondly, we ask, what assumptions can I make? Well, this is a solution. It's in the background showing water, metal hydroxide, and we can notice we've got none of these grey M+ and OH- associated here. They've all dissociated. So when they dissolve, metal hydroxides fully dissociate. And that is just another way of saying separate into ions. So the wonderful thing about that is that because, again, this is a 1-to-1 ratio between the metal hydroxide and OH- ions in this particular case, this means that the concentration of OH- is equal to the concentration of the metal hydroxide which was initially used. So just like strong acids, where the concentration of H+ is just equal to, say, the initial concentration of HCl, you've got a very, very similar relationship here with things like sodium hydroxide. The hydroxide concentration is the same as the initial metal hydroxide concentration. The only thing I would just be careful of is, but be careful of metal hydroxides like calcium and barium hydroxide, where they will release 2 OH- ions per MOH2 formula unit. So you've got to be wise to that, and we'll do an example with one of those later on. So thirdly, what formulae and steps can you use in order to do these calculations? So here's an example. What's the pH of 0.5 mole per decimeter cubed potassium hydroxide? So it's a strong base. We want to try and find the pH, so as ever one of our stepping stones is going to be the H+ concentration, so we can use this Sorensen relationship. And in this case it looked like what we could do relatively easily under that full ionization assumption is to calculate the OH- concentration. So the question then comes as to how are we going to link these two? And the link between them is the ionic product of water. The beauty of the ionic product of water is that because it's an equilibrium constant, if this is a solution at 25 degrees C, we can be sure that that product of OH- and H+ is equal to 1.0 times 10 to the minus 14 moles squared decimeters to the minus 6. And that proves to be extremely useful. So that's the key linking relationship here. Let's solve this and see how it works. So we're going to work out here that the concentration of OH- is equal to the initial concentration of KOH. So that is going to be 0.5 moles per decimeter cubed. Then we can say that if we rearrange this formula, dividing both sides by the OH- concentration, we can say that the H+ concentration is just Kw divided by the OH- concentration. So 1 times 10 to the minus 14 divided by 0.5 comes out at 2 times 10 to the minus 14 moles per decimeter cubed. So then we just stick that in our typical pH formula. Log base 10 of 2 times 10 to the minus 14. And when we stick that in, we get an answer of 13.70 to 2 dP. Here's another example. What is the concentration of barium hydroxide with a pH of 11.23? So we have a quick look. We've got barium hydroxide here. So as long as the concentration is not too high, this should be a strong base. So we can use our typical strong base assumptions here, that the concentration of barium hydroxide, so that's going to be our, so over here is our final step. So this is our concentration of barium hydroxide is going to be simply related to the concentration of OH-. But the only thing here is that we've got to remember that because there's 2 OH- for every one of these, I'm going to need to remember to divide this number by 2, because there's 2 OH- in this formula unit. So how are we going to connect this up together? Well, to get to the OH- concentration, we're going to use Kw, always in these situations. And that will take us from H+. Now why would we want to do that? Well, we've been given the solution pH here of 11.23. So we can start with the pH, convert that into the H+ concentration by doing the reverse of the Sorensen equation, and then we can link this all together quite nicely. So let's proceed to the solution. You may want to have a go yourself. So we've got the H+ concentration is 10 to the minus 11.23. Turns out to be 5.89 times 10 to the minus 12 moles per decimeter cubed. We carry that over to find the OH- concentration. We need to make this the subject, so we're going to divide both sides by H+. And that's going to be 1.69 times 10 to the minus 3 moles per decimeter cubed. And so if we want to work out our concentration of barium hydroxide, initial concentration, which is what the question was asking us, then we just need to take that number and divide it by 2. we get our final answer of 8.5 times 10 to the minus 4 moles per decimeter cubed. And that's a 2SF answer because our pH was given initially to 2dP, which is 2SF. And notice that that's quite a long way below the solubility limit of about 0.3 moles per decimeter cubed for barium hydroxide. So our strong base assumption looks pretty good.